Good morning, good afternoon, good evening, depending on where you are. My name is Jingjing Liu. I'm a researcher and program manager at the Lawrence Berkeley National Lab. Today it is my honor to be invited by Professor Yan and to talk at the Energy Visions and to share our work on benchmarking demand flexibility with all of you. So today I'm going to share some work we have done that's recently published in the Advances in Applied Energy Journal. And this is part of a larger project on grid interactive efficient buildings and demand flexibility. This work is funded by the US Department of Energy Building Technology Office I'm the project lead for over the last few years, and certainly a very important effort joined by many of my colleagues here. So what I'm going to talk about today is to give you a background on grid interactive efficient buildings and demand flexibility in general. And then I'm going to certainly show you this important benchmarking framework that we come up with. But also, as importantly, I want to share some of the thinking behind it, how we come up with this framework, why it looks the way it is, and then going to talk through a couple of I think very significant case studies with a large number of buildings. How do we apply them and to answer research questions? So buildings are getting increasingly smarter these days. They're no longer just the enclosure for human activities and consume energy to provide comfort. Certainly, we ask more of the buildings that are, these are the traits of modern grid interactive efficient buildings. We've been working on efficiency for decades by now, and they're connected with a lot of devices, and those within the buildings, the office equipment or consumer electronics. And if we're not careful, these devices can consume a lot of energy. So energy consumption in buildings could be on the rise if we're not managing carefully. And they're also connected not only with these devices within the building, but also with the grid and a lot of distributed energy resources, or DERs we call, are connected to the buildings, the solar PVs, the batteries, the EV chargers, etc. So yeah, buildings start to talk to the grid. And let's talk about the relationship between building and the grid. So like I said, historically, building only takes power from the electrical grid, and it is however much the building needs to consume, the grid has to provide, and of course the building owners have to pay for it. But with the climate change, there's urgent needs of utilizing more renewable energy, and they're not available all the time. Wind does not always blow, and sun do not always shine. So this relationship is changing, that the grid start to ask buildings to use energy when clean energy is actually available. And this is driving the building's energy use not only has to be efficient, but also have to be flexible of when they use it. And that's what calls for the buildings to be a good citizen on our modern grid. So this is why we're talking about demand flexibility and making the load flexible. The buildings have a role in making the energy more affordable, making our grid more reliable, resilient, reduce emissions, and so on. So when we talk about demand flexibility, what is it? So according to the Department of Energy, the GAB initiative, it is the ability of DERs to adjust buildings' load profile across different time scales. And this is essentially the same as people say energy flexibility or low flexibility. They're essentially the same thing. So talking about time scale, starting with the fast services, and we call modulate. This type of services building can provide, and there has been studies or demonstrations shown it's definitely doable. However, it's not the focus of our study or the GAP initiative for DOE in general, because this type of services have been pretty well covered by batteries and other inverters enabled devices. So really, as a citizen on the grid, again, the grid is really looking up to the buildings to provide load shed type of services and load shift type of services. And then this is because when we talk about decarbonization, which is a really big strategy globally to battle the climate change, we need to move energy use from times to those times when renewable energy is abundant on the grid. So that's a really important strategy. And then for load shed, when there are times the grid has emergency conditions, whether that's a peak load condition or it may not be the peak, but for some reason, contingency situations that really call for the load to shed to avoid massive blackouts. So those are the two types of demand flexibility that we're going to focus in this study. So if you're into the grid interactive efficient buildings, this roadmap is a major effort, is a milestone by the Department of Energy. It was written, led by the LBNL, but also joined effort by NREL and Brattle Group. It talks about certainly, what's the roadmap? What are the work that are needed towards making GABs to scale GABs? And as part of this study, there's a major effort around simulation. So very large scale simulation work have been done. There's some large numbers pointing to the potential of GABs, and certainly demand flexibility is an important part of it. So we just touched on simulation. I want to kind of back out a little bit and talk about, when we talk about demand flexibility, there are three really important areas that we need to understand. So when we talk about demand flexibility and measure them in metrics, what's the magnitude of demand flexibility? And what is the variation of it, or the range of it? And then what are the influential factors? So we're going to talk about all of them today. And in this project, we have used, there's three tools within the researcher's toolbox to understand demand flexibility: simulation, lab testing, and analysis of field data. We have done work in all three areas, but today we're going to mostly focus on the field data part. So like I said, there have been some really impressive work done on the simulation front, but we're still trying to understand what might be the limitations to simulation, because we also have to really check against the real data from real buildings before we make important decisions for our grid and for our society. So that's why we're going to talk about looking at data from real buildings. So what do we really need to learn from the field performance in buildings? Ultimately, the research work we do are going to inform policy making and investments. And that means there will be real consequences of such decisions. And that's why our policymakers and our grid planners, grid operators are often very nervous about making decisions solely based on simulation results. They want to see real performance in the field to prove demand flexibility as a resource for the grid as predicted in these studies. So, so that's why we need to compare performance of many real buildings and extract knowledge from that and understand what drives performance in the field, in what way, and compare it with what we learned in simulation. So that's where the conversation about benchmarking demand flexibility comes in. And talking about benchmarking, let's start with a familiar place. So I trust all of you are familiar with energy benchmarking, and the energy use intensity, or EUI, is sort of the backbone metric behind that. And so what is benchmarking? Energy Star Portfolio Manager is one of the most popular tool for that. And it talks about compare your building's energy to similar buildings, past consumption, or reference performance level. So that is very similar to how we define demand flexibility benchmarking in the paper. We are also comparing the performance of demand flexibility among group of buildings. So some similarities with the EUI benchmarking, we talk about we need one or more metrics. We need a peer group of buildings. And hopefully it's more granular than let's compare with all of the office buildings out there, for example. We're hoping to compare with buildings of similar size, maybe in the same climates, similar vintage, or maybe even similar HVAC equipment, operating hours, so forth, and so on and so forth. You know, when I started my profession, I think granular data like that was not really available. So it really has grown over time. So we expect to see a similar journey for demand flexibility benchmarking. The data set will grow over time. And also, you know, for each building, the performance is not a set value. It can change. It can degrade if we don't take care of it. But if we retrofit, it will hopefully improve over time. So we need metrics for benchmarking. We talk about that and what metrics would we use. So we look into the literature, and in the last 4 years or so, there has been a lot of new studies published. A lot of researchers are looking at metrics. And broadly speaking, we divide them into 2 categories: the metrics that measure at the building level versus those measure at the grid level or the system level. Certainly, we talk about simulation studies, and then there are also some theoretical studies of load shape change, which are still to be proven with real building data, because real building data, as you will see, is very, it can be pretty messy. And then there's another important category of field studies of demand response performance. So hopefully you're familiar with the term or the concept of demand response. Basically, the loads will, what we call shed, basically reduce when the grid call for event. So that's a that is very similar with the shed concept we just talked about. And it is one form of demand flexibility that we are going to use a lot in the study, because that's the demand flexibility, the form of demand flexibility that we have today. So we look into the metrics that have been used in these field studies and have developed this frequency chart. And we selected several frequently used metrics that we thought are suitable for the benchmarking exercise. And the reason we select those metrics are because For one thing, they're normalized, they're suitable for comparing across different buildings, and they have been proven in the previous demand response field studies. And also they're aligned with some of the use cases with our stakeholders, which we'll also talk about. So I want to show you these metrics, what we call single event metrics, in a load shape example. So this is a 24-hour load shape of a building, office building, and this lighter color curve is the baseline load, which means what the load shape would have been if the building did not participate in demand response. And then the darker line is actual load shape, because the building did actually participate in the DR event, which was 6 hours in the afternoon. And so if we subtract the two, we will get this load change curve that you see here. So during the DR event, in this case, noon through 6 p.m., we see a positive value, because this may be counterintuitive because it is a load reduction, but we use the convention from the demand response industry. So load shed is a positive value. And then for this load increase part, because this building did pre-cooling several hours before the event to prepare the building for the DR event. So their energy consumption actually increased for several hours before that event. And we call it load take, essentially load increase. So that's a negative value. So looking at, we have several metrics, but let's just focus on two most important ones. The demand decrease intensity, and the unit is watt per square foot. So we basically take the load shed over the duration of the shed period and average it, and then divide it by the gross floor area of the building. So that's probably the single most important metric that we will use throughout the study, the presentation. And then the other important metric is what we call demand decrease percentage. And it basically takes the average load shed over this period and divided by the average baseline load of this period to get a percentage. So it is important to understand that the reason we call these single event metrics is because that metric only measures a single event, and we can't use it for benchmarking yet, but it is a foundational building block. So we'll show you the benchmarking metrics next. So this is, these are the single event metrics we just talked about, and you will see some connection between the demand decrease intensity, DDI, or the percentage, DDP. They are connected to calculating what we call the benchmark metrics. And among those, the benchmark DDI and benchmark DDP are among the most important metrics in this study. So I'll show you that through an example. We'll come back to this framework to explain the other parts. So here's an example. So in this paper, we presented two case studies. This is one of them for office buildings in California. And these buildings have done resetting their thermostat set point up during DR event by a couple of degrees to reduce the HVAC load. And then for about half of these buildings, they have also done pre-cooling. So the load shape with the for the load shift that we just saw earlier was selected from one of the buildings and one of the events. And then the other half of the buildings only did the load shed, HVAC load shed during event. They did not do pre-cooling. So the single event metric that we just talked about, the watt per square foot load shed, or we call DDI, and also the percentage, let's talk about the watt per square foot first. So for each event, that metric is calculated and presented as a green dot on this figure. So these buildings have participated several events in the year of 2008. And then for each building, we select the 5 highest values among all of the events, and then we draw a box around it. And the mean value, or the average, is going to be its benchmark DDI value, which we'll see in the next slide. So this is the same figure we just saw, and this was the example building we're talking about. It has 5. So for this building, the average of those 5 highest values were averaged to be 0.49 watt per square foot, and it looks like it's roughly 5 watt per square meters. And then there's another building, which, as we can see, it has a larger spread of those 5 values, actually spread pretty wide, from 0 to 0.8 watt per square foot. So average to be 0.36. So as we can see, using this metric alone does not do a very good job of telling the story of that widespread of performance. And so that's the reason we also present this metric of benchmark DDSD. It stands for it looks at the standard deviation. So as you will see, for this building, this metric is much higher compared to other buildings. And of course, this building also have a relatively higher spread. So in general, we want to see consistency in building performance. That makes the performance generally higher and also more predictable. And that's a really nice thing for either the building owner, the operator, or the grid. So, and there are a lot of interesting stories that we can see from this set of metrics. And of course, we also show the context of what is the peak demand intensity or normalized by floor area for that building for context. So again, with this example building, it did load shift. We see that it's roughly 0.5 watt per square foot. And then we look at the peak intensity of this building is 4.2. So that gives us, the black dot is the benchmark DDP, which is the percentage metric. So it's a little bit, it's roughly, let's say 18% of the baseline load is shed, which is pretty significant. And then we look at the load take. This bar represents the average load change intensity during the load take period. And we can see that's a shorter bar. And we also see it's a shorter bar for the take compared to the shed for all of these buildings, which means, at least for this group of buildings, doing pre-cooling on top of resetting the thermostat during the DR event did not increase the energy consumption. And that's a very good thing to see, because essentially we're using the building mass for summer energy storage and improve comfort during DR events. But we have to understand that this sample is relatively small, so we can't really extract that as a conclusion universally. But that shows you an example of what type of research questions we can answer or create a hypothesis using this type of benchmarking metrics. And talking about the percentage for this building example that we see, it is roughly 0.36 watt per square foot shed. And this building had a higher peak demand intensity, 6.1. So overall, the percentage, looking at the percentage of the load shed for this building is roughly 6%. It's a much lower percentage compared to the other building we just saw. So I think it's important to acknowledge that demand flexibility is subject to many, many factors. So there's certainly, what type of building, how old it is, when does it operate, what climate's in, all that. And what we call these cohort factors in the framework we'll revisit in a second, that determines what are the group of buildings, the peer group, that we want to place a building within for comparison, for apple to apple comparison. And then there's a category of factors that will actually change from one event to another. A building may deploy different strategy in different events. The events may be of different duration, may happen different time of the day, time of the week and year, and so forth. The baseline method we will talk about is really important, and also what weather conditions. So these factors, we grouped them and treated them as attributes to the metric values that we show. So it is a really important concept within this framework that we present, that only when we present these attributes that defines under what conditions a metric was measured. Otherwise, presenting the metric value alone would not be super meaningful. And then on top of all this, there are also some stochastic factors. So these are the kinds of things that are kind of random. So we don't really capture them within the framework. They simply show up in the metric values. So here's the framework again. And I think it's important to mention that when we started this framework, or when we started looking at demand flexibility metrics a few years ago, we only had this part. The other part of the framework did not exist at all. We were thinking that we could have some simple metrics to measure demand flexibility, and it did work with simulation. But as we dig into the data from real buildings, we become to realize that it would not work for real buildings. And I'll show you examples of why. So as we just talked about, these cohort factors are relatively static, and we use them to, once we have all the metrics we need, what are the group of buildings we would put together for comparison? And then these are the attributes that what we call single event metric attributes. What are the attributes that will be attached to each of the single event metrics? We'll show you 3 examples. So this is a reality with the real buildings. So we had this very impressive set of retail buildings, over 100 of them, spread across the United States. And we look at the DR events that they participated over the years, and the timing of those events. We realized that buildings located in different states tend to participate in events that are either longer or shorter, or they may also happen at different time of the day, different time of the year. So this means that if we use a fixed metric definition, however long duration we use, then there will be a lot of buildings we would not be able to compare with other buildings just because they have never participated in a 4-hour event or a 2-hour event, whatever is the duration we choose to use with a fixed, if we used a fixed metric. Or it could mean if we didn't pay attention to that and we simply throw buildings together for comparison, then we would not know what we are actually comparing. It would not be apple to apple comparison, because later in the example, we will show you that the event duration can sometimes have very significant influence on the metric value itself. So very similarly with this DR event data set, we also find that not only they vary by geographic areas, but they also evolve over time for any given region, because the needs of the grid keeps changing as we add renewables, EVs, and all the other things we're doing. So that all says that we need a framework that is open and flexible enough to accommodate the changing needs and the varying needs across areas on the grid that call for the buildings demand flexibility. So we have talked about this concept already, that we really have to present the metric values along with all the conditional parameters that defines under what condition did the metric was measured. So use the example to show you that. So the idea is that we would fix most of these attribute values and only vary one or maybe two at a time in order to see how that one or two factors or attribute influence the metric value. Talking about the zero-dimensional benchmarking, so the EUI, the energy benchmarking example, is essentially a form of zero-dimensional benchmarking. So all of the buildings are simply using one metric that they're compared among each other. And so we will use the retail buildings to show you examples of the one-dimensional and two-dimensional benchmarking. It's a very unique approach in our framework. So certainly you can read more about these buildings in the paper, but I'll just mention, it's over 100 sites and across 11 states. These buildings have done something similar to the office buildings that we talked about earlier, which is to reset the thermostat up during their events, in this case by 3 degrees Fahrenheit, to reduce the HVAC load. But in addition, they have also turned off a good chunk of their general lighting in the sales area. And like we saw earlier, what's really unique about this group of building or the data is that the DR events they have participated across the country's different utility programs really varied in their event durations. So starting with the zero-dimensional benchmarking results, we see this is our main metric, which is the benchmark DDI. And we see a very wide range of the value distribution from 0 or negative to about 1 watt per square foot, which is a lot for a building. And similarly, as what you saw with the office example, we use a black dot to show the percentage load shed. So we see it's up to 40%, which is a lot for a building to shed its load. So whenever we see 0 or negative values in load shed, that generally is an indication of either the building didn't shed load, or they could have opted out, or it could have been a baseline issue, which we'll touch on just a little bit later. So, or it can be a combination of both. So what I also wanted to show you is this box plot, which is not required for benchmarking at all, but we use it to show that the boxes represent the top 5 highest load shed values that was used to calculate the benchmark DDI values that you see in this upper plot. But we also see this cloud of dots, which represent the single event DDI values in all of the events. And it has a lot of value in these other data points besides the top values. And we will talk through an example. This is the full set of benchmarking metrics we defined, and I want to point out this standard deviation metric. We see sort of a general descending trend compared to the benchmarking DDI increasing trend. So it seems to tell us that when the building have higher performance, it also generally tend to have more consistent performance across different events, which is very intuitive. And for this group of buildings, we did not see any obvious trend as far as its peak demand intensity in either summer or winter. So let's talk through some one-dimensional benchmarking examples. And this is really important because I think that one-dimensional benchmarking are going to be one of the most useful tools for researchers to understand how a particular factor or parameter or attribute, however we want to call it, has a role in influencing demand flexibility. So this example, the first example, is going to be about the DR event duration. And like I said, this building participated in events that are anywhere between 1 to 6 hours long. So first of all, we take one of the states, this California, and we look at the building level. So each of these group of bars represent a building. And in this example, it has actually participated in events for different durations. And we see a very clear descending trend. As the duration gets longer, the metric decreases. And we see that general trend for all of these buildings. So when we aggregate them by the state, we get a curve like this. So each of the colorful curves represent a state. And then after that, we also further roll it up to be to this dark line, which represent the average across all of the states. So we see that the benchmark DDI metric, it goes down from roughly about 0.55 watt per square foot down to roughly 0.3 watt per square foot. That's a really significant change, roughly 40% decline. So this is why we realized that we need a more open and more thoughtful framework for benchmarking, because we really cannot put the metric from a building that have done a bunch of short events with another building that have participated only in longer events. We just can't compare them that way. So I hope that helps illustrate why the framework is the way that you saw. And here's more examples about one-dimensional benchmarking. So I'm going to go quick on this. So this is looking at the building performance changing over time, so by year. And in this particular example, this group of buildings have done a control upgrade somewhere between 2019 and 2020. So we see a jump in the performance between those years. And also there's only a limited set of buildings have participated in events that actually happened in the evening time frame. So it is a lower shed performance compared to those events that happen during the afternoon. And that's understandable because the building load is declining in the evening. So there's less to shed to begin with. And then we also take a look at one example for two-dimensional benchmarking. So this is more sophisticated and generally requires larger number of data samples in order to make meaningful results. So we're lucky to be able to pull together one example as such, where we not only vary the event duration, but we also add a weather parameter on top of it. And we selected the daily peak temperature for the event day. So so we show the DDI. It's worth mentioning these are not the benchmark metrics, but the single event metrics. We talk about this cloud and how valuable it is. So that data is mapped into this plot where each event gets a dot And the DDI value is plotted against the event duration. But on top of that, we added this color scale to show the peak temperature of the day. So our hypothesis was that, first of all, we expect to see that as the duration gets longer, the shed value decline, which is what we saw earlier. So we verified that trend here. We also expected to see that the highest shed values should happen on the hottest days. And in general, we did see that quite a bit. But that hypothesis is not necessarily entirely true, because we also saw some pretty warm days at the bottom. That means there wasn't a whole lot of shed on those days. So that alludes to the fact that with real building performance, it is more complex. There are many factors at play. So let's take a really quick look at the baseline method. We don't really have time to dig into it. If you're interested, we have published a paper with the ACEEE conference earlier this year talking specifically about baseline method for the case studies that we have done. So we looked at several different baseline methodologies and compared them. And here I simply want to mention two things. Well, we have to be very careful about baseline method. This is something different for real building performance versus simulation. So if we're not careful, if we don't have a solid baseline method, then the metrics values that we use for benchmarking can be very misleading, because this is unlike energy efficiency. Baseline for demand flexibility, if we're not careful, it's very easy to have a pretty significant error. And the other thing I want to mention is when we look at baseline, not only we need to look at the error metrics in measuring how accurate each baseline methodology is, we also really need to pay attention to looking at some actual load shapes for the building, both for the non-event days and the event days, to visually verify with a decent amount of sample to verify that what the error metrics tell you is actually what's going on with the building daily load profile. And then also want to acknowledge that many buildings today have DERs, and we need on-site generations, batteries, EV charging, etc. This framework is still applicable to buildings like these. And the trick is that we will need to get some meter data for those DERs and then do adding or subtraction depending on what it is, on top of the net load that we measure with the building meter before we apply the metrics. So here we show one quick example where a building have PV generation. So we have the blue, which is the net load, and then we added the PV generation to get the building's actual load before using the renewable energy. And then all of the metrics calculation that we talked about will apply. So now I want to start talking about the application. So we talk about this framework. What would we use it for, and who should care about it? So let's start talking about some fundamental benchmarking objectives, and that's regardless of whether you're using it for academic purpose or business purpose. So there's three things that we can do, or three areas where benchmarking could be valuable. First of all, we can monitor the performance over time. So similar to energy efficiency, if we don't take care of it, if we don't pay attention, performance tend to degrade over time. So this will be a tool to monitor that. And also similar to energy efficiency, if we make retrofits and improvements, then we can verify it using we gave an example as such earlier where we saw the control upgrade did actually bump up the performance by a lot. And then secondly, this is also very similar to the UI benchmarking we talked about, that it is really important to compare the performance of a building with its peers to understand what other buildings have done, where you stand, what is actually achievable, and get lessons learned or share best practices. And then third, last but not least, this is really important and kind of unique for demand flexibility benchmarking, is that because we talk about all these factors that are at play, it is important to understand any correlations, and ultimately, how can we better predict demand flexibility performance? So this is the framework that allow us to do. We talk about looking at things at building level and at aggregate level to understand, parameters such as how long the duration the event was, when the event happened, and many other factors. We can use the one-dimensional benchmarking as a tool to understand such influences. So let's talk about the stakeholders who can use this for what and why would they care about it. So there are, for the important players that are relevant to this, there are folks on the building owner side, and then there's the grid side, the utilities, and then in between sometimes there's aggregators. Let's talk about what they would each care about. So for the building managers or even the enterprise property management, certainly we talk about monitoring performance over time. That's important for troubleshooting, and we also talk about they would care about verifying performance improvement after they have done the improvement project. And also we talk about comparing across either their own portfolio of buildings or compare with buildings similar to theirs in general to see what are some of the new opportunities that they could explore. But beyond all that, I want to really stress one of the struggles with the building owners is that it's really hard to predict what the actual performance will be on event day. So what they end up doing often is to sell their service for short, which means they would bid in values that are very conservative compared to their true ability. And during event, they would sometimes sacrifice more on the building services to make sure that to avoid a penalty, underperformance penalty. So that all makes performance prediction really important and relevant for the building owners. And the aggregators have similar concerns because they have a contractual relationship with the grid to deliver. They're accountable, and they are also have to pay their customers. So they are taking the risk. That's also why prediction is also very important for them. So making good dispatch strategy could help them to keep profit. And then the utilities, the grid, when they plan for when they do resource planning, it is important to understand the true performance that can be expected from the building demand flexibility resources compared to the other resources that they that's available to them, and look at the cost and so on. So to summarize all the work we presented today, we first of all, we proposed and introduced a novel demand flexibility benchmarking metrics framework. What's unique about it, we talk about it focused on load shed and load shift, and it has the challenges in real building performance in mind, as you can tell. And this, because we have not only the metrics, but also the conditional parameters, which we call attributes, that allows comparison across many different scenarios. And as you can tell, we have been very focused on using a graphical approach to present the trends, how different factors come into play. And we think that's most useful for stakeholders. And also it allows us to not only look at things at the building level, but also aggregate to gain insights from potentially very large data sets. So we presented the framework through 2 case studies, and we saw with the retail building example, it's over 100 buildings, which is probably the only data set like that I've seen in the literature, so it really fills a gap. And then for the office building group, it's not nearly as large. However, it's also quite unique because it's done load shifting, which is also rare to see in the literature today with building thermal mass and pre-cooling. So these examples have proven that this framework can be applied to even larger scale data sets. It is scalable, and we have shown some key results through these examples. What's the range and variability of these key metrics in the buildings? And also, even probably at least as important as that is show you through these examples how you could possibly apply this framework to the research that you have at hand. And lastly, but not least, we show how this framework can be used by different stakeholders for what purpose, how this would help with their business interests, and ultimately to inspire actions. That's really the ultimate goal of doing research, is not only looks good on papers, but actually inspire actions and make more informed decisions in the real world. So with that, I thank you all for your attention, and this is my contact information if you have questions, and I'm ready for some questions. Thank you.
Yeah. Okay, does anybody has questions?
Yeah, if not, I know it takes a lot of, it's a lot of information, so feel free to go to the paper, digest, and contact me after if you run into questions later.
I want to ask a question. Has
Yeah.
the proposed study been used online?
So yeah, the 2 case studies in the paper are so far, it's really freshly baked. As you see, it was just published online as of a couple weeks ago, and the printing is scheduled for later this year, actually. So I think this group is probably among the first groups to see this work being presented. So yeah, hopefully we'll see adoption, and certainly I'll be presenting this work with other groups in the coming months. So.
Okay, thanks for the reply. And I have another little questions. I'm curious about how does the geographic diversity of the grid affect the flexibility matrix, and how can this be better taken into account in the proposed study?
Yeah, that's a great question. So And I can also just pull up a couple of slides to as we talk to your question here. Give me a second. Just
Okay.
I'll share my screen. So this is yeah, so this is one of the slides where I show that these are 11 different states in the US, and let's see. So traditionally, at least, I'm going to be mainly coming from the perspective from the US experience, and certainly the grid situations can be very different in different countries. But in the US, traditionally, the demand response events typically happen on the hottest summer days when the grid has the highest peak load with air conditioning load. So events are typically called somewhere between noon and say 5 and 6 p.m. And these events can vary from say 2 to 4 or 5 hours long. So a lot of so this group of buildings, we're showing the data of those DR events that they have participated in the last 4 years. And because they're located in many different states, it gives us a lens to see the timing. And we have a couple of slides showing, it used, like I said, it used to be those events tends to be on the longer side, 4 hours plus minus, but now we're seeing events are getting shorter in many states. And also in some states, the timing of the events also are moving from the afternoon when the weather is the hottest to later evening. And this is because, so in California, we have a pretty famous problem on the grid, which is called the duck curve. And it basically, and it doesn't happen on the hottest days in summer, and rather it actually happens in transitional seasons, and especially spring, when there's a lot of PV, solar PV are generating energy. So you would see that on the grid, what we call the system load will have a pretty big dip in the middle of the day because of the solar PV. And then when people comes home, start to, do their laundries or their dishes and watch TV and all that. So the energy use it peaks up in the evening somewhere between say 4 or 5 all the way through say 9 o'clock in the evening. So what we see is a really steep ramping up curve from middle of the day to the evening, and it's so steep such that the traditional generators have a hard time to keep up with that. So that's why we are, in California, we are probably, among the first in the world that we have to tackle this problem, but we're also seeing a very similar trend happening in other states, because everybody tends to have higher electricity use in the evening, and the solar penetration is increasing in many states. So that curve pretty soon, probably, in a few years, won't be so unique to California anymore. So yeah, so that's a big driver for when you ask about the timing of the event. So that's a very big part of the trend. Yeah, does that kind of help answer your question? Do you have any follow-up question on that?
Yes, thank you very much. I think it's very interesting. I got it.
Of course. Yeah, that's a great question. Thank you for that.
Okay, next, if anyone has questions, you can read the article of an engineer later and discuss with by writing to her emails. Okay, considering the time, that's all for the seminar. Thanks for the wonderful report of Engineer Liu again, and thanks to every audience.
Thank you, everybody. Have a good day.
Okay, goodbye.
Bye-bye.